Hello and welcome to this programming skills lecture on tools for code analysis, code browsing and performance analysis for your programs. Today what we're looking at is things that you can use to look at source code that other people have given you, so sort of moving beyond just starting developing and writing your own source code to moving into a situation where people have given you code to alter, to optimize, to use. What can you do to get your hands on, understand and play around with this code, and then are there tools that we can use in the development cycle to give us some insights into things that may be going wrong or things that maybe need change. So just like we have compilers to help us check whether our programs are language compliant, standard compliant, there are other tools out there which we can build into our development process or use in our development process to help us improve our development, improve our coding, improve our productivity. And then looking a little bit beyond that at, okay, we have a correct program, we're happy we understand it, can we now look at performance and look at optimizing it? So as I say, we'll look at some tools for browsing, and I will discuss some tools for browsing and analyzing software, and then some tools for profiling software and understanding performance of software. And then at the end, slightly off topic, but we'll talk a little bit about presenting results from optimization or other kinds of results, because whilst not strictly programming skills, it's always useful to understand how you should present results and what the pitfalls are, particularly for things like the coursework or other courseworks. So by code browsing and analysis tools, we mean software which helps us understand applications. So understand going forward. So that could be reformatting, that could be highlighting with colours, that could be enabling you clicking through, etc., etc. Now, this may sound unnecessary, not required, particularly if you've spent a lot of time developing small applications, because if you've written a couple of hundred lines of code in a single file, then you don't necessarily need any tools to help you understand or look through or get a handle on what's going on there. But of course, in real life, in work, you tend to have much more complex and much larger codes to deal with. So you can easily be dealing with codes of tens of thousands, hundreds of thousands, millions of lines of text across many files, including different libraries, including all sorts of different functionality. So it's useful to know that there are tools out there which can optimize your development process or help you with your development process. And actually, we've been teaching this kind of ideas for 15 years now, and when we first started teaching this kind of stuff, this was quite new to a lot of people. So people would have been doing programming with reasonably basic text editors most of the time, and of course in today's modern development environment, people are much more used to using integrated development environments and full products for code development. So this is not necessarily particularly new news for many people, but if you've not come from a background of developing programs, it's worth knowing that there are things out there which often make your code development much simpler. So there are a range of different things that these tools can do for you. So it's along the lines of understanding the code syntax, but so that's showing you functions, how they're structured, maybe using different colors to highlight arguments to functions and return values and keywords and these kind of things. But these tools go beyond that, so they can do things like show you a call tree or a class hierarchy, so you can understand which functions are called from elsewhere in the code, which classes are used elsewhere in the code, and then they can give you tools or little options to go through and make changes in your code. So if you are, for instance, developing in an IDE, in an integrated development environment, then it's certainly possible to say, okay, I want to rename this function here. Please, can you go and rename it everywhere in the program, so I don't have to manually go through and do that. And that can be very, very time-saving, very useful functionality, and even moving into a debugging arena, so we can use some of these tools to look what inputs and outputs functions have, and try and work out where data might have changed in a development cycle or in a run of a program. And so these, as I say, go from a whole range of things, from development environments like Eclipse and Clay Code, and there's a number of these, Xcode, there's a number of these out there, to much smaller little bits of software like OO Browser or OpenGrok, which are not full development environments, but tools that let you browse through the code and have a look what's going on. One of my simplest but favourites is something called F90 to HTML, which takes Fortran 90 programs and turns them into web pages. And it's not a development environment, you can't change the code through it, but it does let you load up all the code and then click on functions to see where the function calls, to see where those functions are defined, click on different modules and that kind of thing. So if you're working in an environment where you don't have the full tools, that can be quite useful. Now, this isn't designed to be a complete list of these softwares. There's lots more of them out there, and as we've seen, hopefully, the debugging tools in previous lectures and in practical, you can get similar kind of functionality just using a debugger, not to help you develop code, but to help you understand what bits of code are called where. If there's a particular part of a functionality which you're not understanding, you could run the code, put breakpoints in and see what's called. And for more complex programming languages, where particularly the object-oriented programming languages, where we have multiple inheritance and we have function overloading, just looking at the source code doesn't necessarily fully tell you exactly what's going to happen, because it very much may depend on what data types you're using as to exactly which versions of a function or a routine are called. So integrated development environments are generally quite good at letting you look at these and choosing the most sensible functions, the most relevant ones, but sometimes getting down and actually running the code, running a C++ code in a debugger to see exactly which version of that function was called here can also be useful. So beyond that, but not full integrated development environments or full code browsing tools, there are a set of little functional tools, little programs which can help you in your development cycle. So code analysis tools, much less than full development environments, but particularly for the compiled programming languages like C and Fortran and C++, can give you some information or some insights into your code. So for instance, here we have an example of a little bit of C code. At first glance, certainly to me it looks pretty correct. It's a very small piece of code, it's not doing anything complex, but I can see that it's taking a variable, it's looping over it, it's adding it up, and if I run that through most compilers, this code would compile fine and I could run it, but actually in reality it's not correct code. So if I take a code analysis tool like lint, here's a top example, it's checking the correctness of my C program. So it's looking at not just is that correct C you've written, but looking at some of the other issues beyond that. And I can see that in this case it would give me a warning to say variable may be used before set. And indeed, if we look back at this program, I can see that I'm adding data into A as I go around that for loop, but I've never initialized A to 0. So it's giving me a warning. It's saying, did you mean to do this? Because if you haven't initialized A, then you may not get the correct answer here. And then it's also telling me some other things. So it's here saying function printf returns a value which is always ignored. There's too many arguments for printf, and both of those are true. Printf is a function which lets you pass in as many arguments as you want, so it has a special kind of definition, and that confuses it. But also printf does return an error code to say whether it completed correctly or not, and I am ignoring it in this case. If I wanted to see that error code, I would have to say something like I equals printf. But I don't need to worry about it. I know that if the thing doesn't print out on the screen, the likelihood is that it's failed, so I don't need to check the return code there. And there are other kinds of these examples, so something called Flint for Fortran, or FTN check for Fortran, cscope for C, CPP check, Splint, cscout, lint for J, JLint, find bugs. Those kind of little tools can be useful, because you can put them into your development cycle, you can add them to your make file, do you build scripts. You say, okay, I've finished my development, I'm going to build this program, but first check it and tell me if there's any errors. Run my source code through these scripts. So that can be useful, and there are more functional versions of these similar kinds of programs, but that do different things. So CFlow or CXRef can be very useful in generating call graphs of programs to show you what function is called where, and indeed in CXRef's case, what variables are called where. So it'll go through and it'll say where data is updated and where data is moved. And that kind of thing. So that can be useful in saying, oh well, I know I've got a problem with variable A. Okay, can you tell me where A is set? Can you tell me what line it's there? Is it where's it read? Where is it updated? Where is it stored? These kind of things. You have to be a little bit careful with these kind of C tools, because you can see here at the bottom here, I'm still using this same program back here, this small little 10-line program, and you can see CFlow gives me a very simple printout here. It's just saying there's a main loop. It starts at this point in my source code, and it calls one function called printf. That's all it's doing. If I run through CXRef, it does something more complicated. It says there's a function, but there's also these variables, and these variables get updated or read in various places. But actually CXRef does much more than that, because my original source code here includes a library. It also goes through and tells me all about that library and all the things that are defined in it, and actually you can't see off it all the things, but that single 10-line program on CXRef will produce very large amounts of output. So you have to be a little bit careful with these tools. They don't always give you exactly the output you want first time. The compiler, so likewise, the compiler is actually usually quite good at picking up some of these kinds of issues, or doing correctness checking on your program. Certainly it will check your program against a language standard. That's its job. But also you can get compilers to tell you some of the things which are more like warnings. So for that program before where I didn't initialize my variable, you can see here at the bottom, if I use the Cray compiler, it would tell me, okay, you haven't initialized your variable. Did you mean to do that? So some compilers will do these kind of things. Here we can see that the GNU compiler, when I turn on all the warnings and the pedanticness, it's still not telling me about that variable not being initialized, but it is telling me some other things. So it's worth looking for your compiler documentation and seeing what kind of checking it can do, and working out how to turn that on. And in this case, for GCC or gFortran, I can use this -w all, so that's warn all, and -pedantic to say, really stick to the actual language standard correctly. So those are tools to look through source code and do some checking and helping with development. And it's very useful to have a look around what's out there, have a chat to other people and see what they're doing, and see what you can build into your development cycle to help you with these kind of things. As I already said, once you've got to a point where you're happy, your program is correct, does what you want it to do, you may then be interested in making it more performant, optimizing it, making it run faster. Now, of course, this isn't true for all development, so there's a whole wide range of code that you might write where you may not care about performance because what it's doing is fast enough for what you need and you don't need to spend any extra time optimizing it. And so if you look around there and you just talk to people, there are a lot of people who will tell you, for a lot of development, don't optimize, don't look at doing this, focus more on writing correct, understandable, maintainable code, not the fastest code, because actually you'll spend a lot more time fixing bugs, extending code, these kind of things, than you will caring about optimization and performance for the development that you're there doing. And of course, Donald Knuth has this famous quote that you should forget about small efficiencies, so you should forget about optimization 97% of the time, because premature optimization is the root of all evil. Changing code or writing code in a way that you think is optimized will often end up producing poor code that's hard to understand, code with bugs in it. So you shouldn't set out with a chance of writing strange code because you think that's going to be the most optimal. You should write straightforward, understandable, testable, documented code. And then at some point, what you want to then go do is come back and look at optimizing the bits of the code which are used the most often and the bits of the code which are slowest. So, as he said here, what you want to do is come back and look carefully at the critical code, but only once that code has been identified. And this is what profiling does for you. And then somebody called Michael A. Jackson, not Mike Jackson, who is in charge of his course, but a different Mike Jackson, says the first rule of program optimization is don't do it. The second rule of program optimization for experts only, don't do it yet. And again, that's referring to the idea that before we go and try and improve the performance of our programs, we need to understand the performance of them first. So we need to do profiling. Discover if your program is quick or efficient or not on the hardware you're running on. Discover where time is being spent, and then you can focus on optimizing the important bits. And quite often, even if you've written some code, the bit of code which is most expensive in terms of computational time may not be the one that you think it's going to be, right? And it may change from machine to machine. So what we want to be able to do is take our code, profile it to work out where time is being spent in the code for a given test case, and then optimize those bits which take the longest amount of time. So if I can see, okay, this one routine is accounting for 70% of a runtime, then if I optimize that, I'll have a big impact on the overall code. If I spent a year trying to make a routine that only took 10% of the overall runtime faster, I could make it infinitely fast, and I would still not save my overall runtime very much. So we want to do profiling so that we can work out if we need to optimize the code and then where we need to optimize the code. So for profiling, we can use a profiler. So it's a tool or a set of tools that let us analyze the performance of an application when it's running. So general standard profiling is generally done by the compiler, in the sense that you tell the compiler to add in some extra code into your compiled executable, so that it records some more data about what your program's doing when it's running. So this could be recording every time a function is called. So at the end of a program run, we know how often a function has been called, and we know how long each one of those function calls took, so we can work out which were the most expensive functions, which were the functions which are called the most, and target our optimization using that. We could also look for more specific things like hardware counters, specific hardware issues, or even doing sampling, which is run the program for a bit and stop the program running interrupted, and go and look at exactly what instruction was being run when we interrupted it, and then start it back up again. So not just looking at what functions called, but looking inside the functions and looking exactly, what are the most common lines of a program, what are the most common instructions that are being called. So those are the sort of options we can have. Now, this doesn't come without a cost, so we're adding extra stuff into our program which will take more time to run. So profiling has an overhead. Profiling will make your program slower. That's why we don't have it turned on by default. That's why we don't have it turned on all the time. We just turn it on when we need it, and then we turn it off again. And the actual impact it has depends on exactly what kind of profiling you're doing and what the structure of your program is. If you have a small program with not many function calls, but each function call takes a long time, then the profiling, if you're just looking at how many times those functions are called, might not be very time consuming. If you're wanting to interrupt the program and check what instruction it's writing, it's using very frequently, then that's going to add a big overhead onto your runtime. Okay. So the standard Linux Unix profilers, the ones which just track how often functions are called and the time that those functions take to run, are called prof and gprof, and they are enabled, or the data that they use is enabled by compiling your code with -p or -pg. So you build your code as normal, but you just add the compiler flag -p for prof or -pg for gprof. Prof is a bit simpler. It just will give you a single output of the top functions and how much time they spent and how often they were called. Whereas gprof will also give you some of the call graphs, so which functions were called from where inside your program. So you compile your program with -p or -pg for each source code you want to profile. So each source file you want to profile. And then when you run your program for a given test case, it will produce something called mon.out if you compiled it with -p, or gmon.out if you compiled it with -pg. And so after you've run your program and it's generated the profile data, you can then use the tool gprof or prof to analyze the performance. So you'd then type gprof and then the name of your program, the name of your executable, and it will go and look for the gmon.out file which matches that, and it will display something. So here's an example of a prof tool. I've run it on a small program which has got something like 4 or 5 functions in it. Doesn't run for very long. I compile my program with -p to start with, and then I ran it, and then I did prof my program, and it looked for the mon.out file, and it produced me this. So I can see here that I've only got a small number of functions. There's one called relax, which accounted for about 32-33% of the total runtime of my program, and one called resid, which accounted for something around 28% of the runtime, something called _F90_close, which took about 11% of my runtime, and then some other things going on down here. So I can see here that actually, if I could optimize these two programs, these two routines up here, and make them faster, I could have a big impact on my overall program runtime, because that together they would be about 60% of the overall runtime of the program. I can also see that some of these things may not actually be functions I've written myself. These are probably more coming from the library, from the Fortran language, which is a Fortran program in this case. So these are probably file operations defined in the Fortran language or in the Fortran implementation I'm using. And there's a couple of other things we can see here as well, because so it's telling me how long each function ran for cumulative. So the relax function, it ran overall for 0.71 of a second. It was called 14 times. So if you divide 0.71 by 14, you get, it was 50 microseconds per call. And I can see some other things over here. So some other functions which were called much more often, didn't take up much actual runtime, but were called many times, including this one here called mcount. And actually in this case, mcount is the profiling function which the compiler has added in to get me this data. So I can see here that running this program with this -p compilation to turn on the prof output has added about 6% onto the runtime. Well, 5 or 6% onto the runtime compared to what it would have been if I ran without profiling. So if this actually appears in your program, so quite often something like this doesn't appear in your profile because your program is running for longer, it's not very important. But if you do get something like mcount or mon control or monitor or something very high in your profile, if it's taking up a lot of time, that can actually indicate that your program has a high function call overhead. Means that you have lots of small functions being called, and the very process of just calling functions is taking a lot of runtime. So you probably want to refactor that code to get rid of a lot of small functions and merge them into some smaller, bigger functions. Sorry, some bigger functions that are called less often. But yes, gprof will also produce something similar, but it also, as well as this kind of output, it would also tell me where each function was called from. And it's not just C and Fortran and C++, those kind of languages we have profilers for. There are also profilers for Java, so what the profilers for Java tend to do is connect to the JVM which is running code, something like JProfile or Gensor or JVisual VM, those kind of things, and do some analysis and some interaction with your running code. And Python has a fair bit of profiling functionality available for you. So Python has some built-in profilers, cProfile, for instance, or Hotshot. And so when you run your Python program, you can actually say, okay, run with this kind of profiling functionality turned on at the command line like this. Or you can do it inside your program and then profile and then say, actually, I want to profile this particular function, this particular subroutine. And then there are some nice performance visualization tools available to interact with profiling data you get from Python. Beyond sort of lightweight and reasonably basic profilers like prof and gprof, and there's a whole variety of more complicated, more functional profiles available. A lot around parallel programming, so things like Tau and a linear map and Graypat. One's something like Vampire-Trace for MPI profiling. These are sort of beyond the scope of this programming skills course, but there's plenty of documentation out there if you're looking to do large scale profiling of parallel programs. Some of these tools can be very useful. They tend to be more graphical, others command line. Intel have one as well called VTune, so there's a whole bunch of them out there. And also it can be very useful to, when you get into in-depth performance optimization, start looking at hardware counters. So how efficiently you're using specific processors, and there are different ways of doing this. Again, it's beyond the scope of what we're doing in this course, but useful if you're going to do more optimization work in high performance computing or in data analytics or machine learning. So the PAPI library is one way of interfacing with hardware counters across a range of processors. AMD have their own tools, Intel have their own tools. So these can be quite interesting. Interestingly, it's one of the areas where ARM processors are a bit weak at the moment. There isn't much in the way of counters and access to a wide range of hardware information yet, but it is coming. And then, of course, you can do your own profiling, i.e. adding timers inside code directly to work out exactly what time is being spent in different parts of a program. So you can use things like dtime and etime in Fortran, system clock or get time of day in C, or things like MPI time can be quite useful if you're writing MPI programs, in parallel programs. So there are a bunch of other timing routines you can use. You have to be a little bit careful with timers because they can change from system to system, the resolution, how accurate they are, and exactly also what they do. So, you can have timers where you think you're getting the wall clock times or how long a program took to complete, but actually it's summing it up across threads or something like that. So you do have to be a little bit careful, these kind of things. And then there are very simple things. So the time program in Linux will just tell you, it won't profile your program. It will just tell you, okay, this is how long the whole thing took to run. So in this example here, it took about 2.3 seconds of user time, about 0.2 seconds of system time. But it looks like it was a parallel program here because the real program, it reckons it took about 4 seconds, so it's using a couple of threads to do some work here. But that can be useful here. So yes, there are tools out there which are useful and will help with your productivity and help with your development of software and of programs. And so go out and find some, play around with them, see what works well for you. Use a development environment, build in some of these little programs for checking correctness and checking functionality in programs. That can be very useful. And then when we get on to optimization of applications, then profiling is what you want to do before you try doing anything else. So get to a point where you profile your code, so you understand the performance of it before you try optimizing it.